This is the demo presentation from Group 8. Our project is a response to smart city disasters. The goal of this project is to develop an application that simulates responses to disasters in Dublin City. A disaster can be reported at any location of the city, and then our application will mark the disaster area on the map, send emergency vehicles such as ambulance, police car to help affected people, and plan evacuation routes from the disaster zone and to the assembly point. The two major components for the system are the client and the server. We have two kinds of clients, vehicles and our self-developed Android app. Vehicle clients simulate emergency vehicles and constantly update their locations to our system for monitoring and display. App clients are able to do disaster information management and vehicle requisition management under circumstances where internet is available, and do peer-to-peer communication under circumstances where internet is not available. Details of our application can be checked with the other demo video. Our server are also composed of two parts, the stateless web server cluster and the RaftDB cluster. The stateless web server cluster connects between the clients and the database server to perform data validation and route planning upon request. We would like to highlight a few areas in our project: peer-to-peer, stateless server cluster, and Raft database cluster. In these areas, we met serious difficulties and trade-offs. We would like to explain them in details. The reason why we need to integrate peer-to-peer network to our application is because one of our scenarios requires our application to work in the disaster area where there is no internet connection. There is no working infrastructure, and any connection point could be joining or missing at any time. Therefore, our network requires scalability, and there should not be a critical point. So we choose a peer-to-peer network structure, which could allow minimum communication between devices within a certain distance, even if there is no internet access. But a peer-to-peer structure has weakness as well. The structure is not robust, the connection is not stable, and the performance of each device is not equal, which may cause propagation delay in the network. Peer-to-peer discovering process also costs a lot of power. The two options we had for implementing our own P2P network was P2P Direct and P2P Wire. After careful consideration, we chose P2P Direct because it has better compatibility and the development document is more detailed. Our distributed stateless server cluster connects between the client and the database. We can have multiple instances of the server in the cluster, which improves availability. Adding and removing instances from the cluster is also easy, which makes the system highly scalable. There are three key features with our server cluster. The first one is high availability and scalability, which is implemented with distributed stateless server nodes. The second one is automatic load balance, which is implemented with Nginx load balancer. The third one is concurrency control, which is implemented with distributed lock with Redis red lock. We had two options for implementing high available and scalable server clusters. The first one is stateless server cluster. The second one is wrapped server cluster. But why did we choose stateless server cluster? Because the major requirements of the server are data validation and route planning, which does not require stateful service. Since stateless server cluster can satisfy this requirement and is easier to implement than wrapped server cluster, so we chose stateless server cluster. We also had two options for automatic load balancing. The first one was Nginx. The second one was AWS Elastic Load Balancing Service. After careful consideration, we chose Nginx because it's very easy to use. Just put a few lines in the configuration file and everything is all set. And also because it's free of charge, which is very friendly to student projects. For concurrency control, which is basically write and read log to the database server, At the beginning, we were thinking about using Redis setnx, but while we were researching about it, we found out about Redis Redlock, which, according to the Redis official documentation website, offers better guarantees and is fault tolerant. So we upgraded our original choice. Our database service, RDoc, is a highly available document database. Every database instance will have a database object, and the database object can contain multiple collections. A collection could have an index object and multiple documents, where the document is the basic data structure in our database. We use Raft algorithm to improve the availability and scalability of our database cluster. When the cluster starts, they will use heartbeat timeout to elect leader, and different nodes will have different heartbeat timeout to avoid election collision. A node needs to get majority votes to become the leader. This will guarantee that there is only one leader in the cluster. The leader will process all the commits. It will ensure that every node will have the same commit in the same order. Whenever there is a node failure, the leader will retry until the commit is stored by all the followers, and the commit will be considered successful if majority nodes receive the commit. The leader will be responsible for log replication using Red Hat log. Whenever there is a new leader in the whenever there is a new follower in the cluster, the leader can use its local log replication to recover the data in the new follower node. With these techniques, we ensure the data consistency in the database cluster. That's all about our project. Thank you very much for listening.